All right, mathletes. So this is our last unit, and we're going to take one more stop in chapter 4 in the book. But this is the introduction and the start of our study on integrals or integration. And and so basically, antiderivatives are basically what an integral is. It's just the opposite of a derivative, right? It's the kind of the inverse of a derivative, if you will. That's that term's used a little loosely in this case, but you'll see kind of the relationship between the derivative and the integral here, and you'll see the introduction of the integral symbol and things like that. And so anyway, I think hopefully you'll find this pretty intuitive. So if you have a function capital F of x, and I use capital F just because that's commonly used in this case for the antiderivative. But if I have this function capital F of x that equals 6x cubed minus 5x squared plus 11x minus 2, then the derivative of that, like let's say if I try to find f primed of x, then of course that would be 18x squared, right, minus 10x plus 11, and then this 2 would go away, right? And so this would be this function here would be the derivative of this function, right? And let's say that I called this function just regular f of x, okay? So then this function here would be the antiderivative of this function, okay? So this function is the derivative, this function is the antiderivative, all right? So it's basically like undoing the derivative, right? Now the tricky part of it though is if I said, how do I get from here to here? You could get everything but one piece of that, right? There's one part of that if I gave you this only, there's one part of this that you wouldn't be able to find. You know what it is? That's right, the constant. If you said the constant, you're exactly right. There's no way I could get that -2 by just looking at this, right? So if I were to be given this and asked to find the antiderivative, like if I was thinking, okay, what function could I derive to get this value? There's actually an infinite amount of them, right? Because I could get the 6x cubed, I could get the negative 5x squared, I could get the 11x. Like those are the things that I would have to derive to get those values. But there's a lot of things there are a lot of constants I could tag on the end and still get the same thing, right? Like I could have 6x cubed minus 5x squared plus 11x plus 0, right? And not have anything here. Or I could have a plus 1, and if I derive this, I would still get this, right? Because the derivative of 1 is also 0, right? I could put a 10 here. I could put any number, right? There's any constant. I could put pi here, right? Derivative of pi is 0. Any constant could go here, right? And so what we do is, instead of trying to guess at a constant, or instead of leaving it blank, we just put plus c, right? Plus a constant, because we know that there could be any constant there, including 0, including a negative, including a positive, rational, irrational, etc. Any real number could go there, and we don't know what it is, right? There's no way of finding it based on just being given the function alone. And so we put plus c, plus a constant, okay? All right. So the antiderivative is basically the reverse of the derivative, okay? All right. So here's some kind of some of the math terminology here, the technical terms, but this is just kind of saying the same thing. Here is that f is the antiderivative of f. So the function capital F is the antiderivative of lowercase f if f primed equals little f, right? And that's what we just saw in that last one, right? So so if f primed equals little f, then regular f of x is the antiderivative of little f. Okay. All right. And then the form of the antiderivative. So here this is talking about why we add the constant, right? So f of x plus c is really how we write the general form of the antiderivative, right? And it's general because it can cover any function, right? Like here, we're basically saying that not only does f of x plus c work as an antiderivative, but also you can have any other function where you have any other constant, and that's also an antiderivative of that, right? So we saw on the last page that we could put any value here and make a new function, and it would still be an antiderivative of this, right? Like this is a specific one that we happen to know at the beginning, but I could put I could put any value in for c and have an infinite amount of functions that I could derive to get this, right? And remember, by the way, that adding c here, what that does is it doesn't change the shape of a function, it changes the location of a function, right? Like this is the y-intercept of a polynomial in this case. And so, so like, for example, this one would cross here, right? And it would have some kind of shape, a cubic, could have some kind of shape like this, right? And so, and that's not exactly what it is. I'm just making this up at this point. But if c was 3, then it would cross right here, right? And it would be the same shape. It would just cross at a different point, right? And so this doesn't change the shape of the function. It just changes the location of a function, right? It just moves it up or down, basically. And so there's an infinite amount of functions like, up or down, that if I derived them, I would get this. And so that's what this is saying here, is like the antiderivative. It could be any function, or it could be this function plus or minus any constant, right? And so yeah, so they're just saying that you could have another function that is also the antiderivative of f. All right, so this is the general form, because this kind of covers all the possible antiderivatives, because we're just adding that variable constant that could be any value, any real number.